Welcome to Excel 2013 Statistical Analysis video number 70. Hey, if you want to download this Excel file to follow along or the PDF file, click on the link below the video. Hey, we're in Chapter 11, and Chapter 11 is about the inference for the difference between two population proportions. Now, last chapter, Chapter 10, we talked about the inference for the difference between two population means. But means are not the only numbers that we want to compare and see differences. Sometimes we have proportions. Now, the main example we did in Chapter 10 is we were interested in whether two population means were different, right? Means. And our example was we had the mean income in Bradford, that's a city, was $38,010, and the mean income in Kane was $35,006. And since this is sample data, these are sample means, when we get a difference, the question is that just sampling error, or is that a significant difference where we can say there's a difference between these two? These are all actual numbers, meaning we went out and got a sample of dollar amounts for income. We calculated the sample means here and calculated the difference. But now, in Chapter 11, we're interested in whether two population proportions are different. Our example will be, we'll go out and get sample data for data entry. And in the year 2013, data entry error rate was 0.42. That means we went out and we sampled data entry and checked whether there's errors. If there was errors, we had a yes. If there weren't any errors, we had a no. So we'll have a data set filled with yeses and nos. Remember, we had to use like count ifs to count how many yeses, and that's the answer, 14.2%. In 2014, the data error entry rate was 10.7. So there's a difference, and this is sample proportions. We take the difference. The question is, just like in last chapter, the question is, hey, is that difference due to sampling error, or is it significant enough where we can say there is a difference between data entry errors in the year 2013 and 2014? So Chapter 11 is all about proportions. Now I'm going to hit page down in the PDFs, because I want you to remember proportions from Chapter 7. A sample proportion, Pbar. Hey, we have some x and n. The x is simply the number of elements in the sample that possess the characteristic of interest. X is a categorical variable. So our first example will have yes and no. And the x we're interested in is yes. N is the sample size. So when we count how many yeses, we compare it to the sample size. And boom, we get our Pbar, or sample proportion. Now, if you remember, sampling distribution of Pbar can be approximated by the normal distribution whenever two things are true. Sample size times our P, or Pbar in our case here, because we're going to be using sample data, is greater than or equal to 5. And n, and then we have 1 minus P, or if you don't have P, you use Pbar. If that's also greater than or equal to 5, then we're allowed to use the normal distribution. Now, we talked about the sampling distribution of Pbar in Chapter 7, but we actually didn't go through the whole process of constructing a sampling distribution of Pbar. In this video, we're going to do that. Now, all we said back in Chapter 7 was, hey, the expected value of Pbar. That means if we went out and got every single combination, every possibility for our samples and calculated all the proportions, if we took the average of all those, we get the expected value of Pbar. And guess what? It would be exactly equal to the population proportion. We're actually going to do that calculation, list every single sample, or calculate every single sample proportion, and then calculate the average. And lo and behold, we'll see that it's equal to the population proportion. Back in Chapter 7, we also had the standard error, or standard deviation of the sampling distribution of Pbar. And here was our formula. P times 1 minus P divided by n. And then you take the square root of that. if we happen to have a situation where the textbook doesn't really have this situation many times. But if you have a situation where sample size divided by population size is greater than that 0.05, then you have to use this correction factor. All right, now I want to go use the keyboard page up to jump back. And actually, a strange thing about these PDFs, I added one to the beginning, page 0. So I actually have page 0, page 1. I don't want to look at page 1. Chapter 11, here's all of the topics. We're actually going to do confidence interval and hypothesis test for the difference between two population proportions. Then we'll see what to do when we have a hypothesis test to check the equality of 2 or more. Now, the textbook says 3 or more population proportions. I just put 2 or more because you can use the same test for 2 or more. Most of the time, we're using 3 or more. In our example, we'll have like 4 or 5 population proportions, and we want to check the equality. And guess what? We're going to use a brand new distribution called the chi-square distribution, and we'll use the chi-square test statistic. We'll also see at the last video in this chapter, we'll do something called a test of independence for 2 categorical variables. Now, before we jump over and actually construct a sampling distribution of Pbar1 minus Pbar2, remember last chapter we had sampling distribution of Xbar1 minus Xbar2. This is the probability distribution of every single difference. Remember, Xbar1 minus Xbar2. And last chapter, video 63, we actually listed every single difference and then proved our 2 formulas, that the mean equals expected value for all of the X-bar differences. And we proved that this little formula for our standard deviation standard error works. Well, we're going to do the same thing over here. Oh, sampling distribution of Pbar1 minus Pbar2. Hey, there it is. If our 4 tests are passed, we get to use a normal distribution. But we're going to actually go out and construct this, and it is the probability distribution of all possible values of Pbar1 minus Pbar2. And we'll plot it on a chart and see that it's basically symmetric. We'll also prove that expected Pbar1 minus Pbar2 will be exactly equal to the proportion from the first population minus the proportion from the second population. And then we'll have our new formula here for standard error or standard deviation. And this one is for the sampling distribution of Pbar1 minus Pbar2. And we'll actually prove that this formula works. All right, so now I want to go over to Excel. Now we're on the sheet sampling distribution of Pbar1 minus Pbar2. Our goal is to create this distribution of Pbar1 minus Pbar2. But because we didn't back in Chapter 7 look at just a single population, list every single sample possible, calculate the proportions, and prove that the actual expected Pbar, that means the average of all the sample proportions, is exactly equal to the population proportion. We're going to do that here. Then we're going to take 2 separate populations for proportions. Here they are. And we're going to plot every single difference and prove those formulas. All right, so let's go ahead and do it. And you can imagine this is categorical data, yes and no. So in our bigger example we'll do later, next video, we'll do error rates. So we could imagine these are error rates. So in the sample of size 8, we found 2 errors in the documentation. The other 6 sets of documents had no errors. All right, so we're first going to calculate the population size. We're counting text, so I'm going to use count out, which counts not empty cells. So there we go. We have a yes and a no, our only 2 options. Our x we're interested in is yes, but I'm going to count both of them. So count ifs. And our criteria range, I highlight the whole population and F4 to lock it, comma, and my criteria is relative cell reference 1 to above. So I'm counting how many yeses there are out of 8. Now I'm going to copy that formula down. And of course, absolute and relative works. Now we only have 2 different possibilities for our variable here, yes and no. Sometimes we only count the yeses, and then to do 1 minus p, that would be the complement. Here, we only have 2 possibilities, right? So when we go to calculate proportion from population 1 of yeses, I can simply say, hey, There's the 2 divided by the total count, big N, and I'm going to lock it with F4. Control Enter. And now, of course, that formula with its relative, getting the no count of 6, and the 8 will calculate the proportion of no's, or 1 minus p. Now, our sample size down here is going to be 1, but I want to figure out the total combinations. Remember, our population size is 8, and each sample is going to contain 5 of the items from our full population. So I'm going to use the combin function, as we've seen a number of times already in this class. Hey, there's the number, comma, and they call it number chosen. There it is. That's the sample size. 56 combinations. Now, what do we do when we look at a population and list every single possible sample? Well, 1, 2, 3, 4, 5. That's exactly yes, no, 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 no. Well, if I was doing it manually, I would then have to go like this. Yes, no, 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 and then go get the next one. And that's what's listed there. Then I'd have to do exactly the first 4, and then the second to last one. That's exactly what's listed there. And so on, right, until we get this. In Chapter 7, we showed some code we got from the internet that automatically took a set of population items and listed every single sample. But hey, now we need to calculate our sample proportion. Now, if you remember, last chapter, Chapter 10, and Chapter 7, we had numbers, so we used the average function. Here we can't use average. We have to use countifs. And I'm going to first count from a relative range, 5 to my left, comma, and I'm going to look at the criteria yes, and that needs to be locked, so I hit F4. Now, right now, if I enter this, all it does is count 1, F2 to put it back in edit mode. But every time to calculate the proportion, I need to compare it to our sample size of 5 up here. So I'm going to lock it on D8, F4. And that will calculate the sample proportion. Control Enter. 0.2. Double click and send it down. Control down arrow gets me down to the bottom, and you can see I have all 56 of those samples, and there's all the proportions. Control up arrow. Now, let's do it. Hey, what's our population proportion for yes? It's 0.25. So I'm just going to relist that here, because the exciting part is enter right here. Remember, we're trying to prove the expected value of Pbar. That means this whole distribution of every single possible sample proportion. If I take the mean of all that, it better be exactly equal to the population proportion. Click on the top cell, Control Shift down arrow, and I'm going to Shift Enter to put that in the cell and jump it up. And sure enough, the average of all our sample proportions is exactly equal to our population proportion. This is the mean of all the sample proportions. Now, that proves the first little part. And if we go back to our PDFs, now on page 2, all we did was prove this little part here. Now we want to go look at the second part, the standard error, or the standard deviation of the sampling distribution of Pbar. All right, so now we need to check for our 0.05 equals sample size of 5 divided by 8. Of course, this is going to be huge, so we have to use the correction factor. The correction factor is this part, and I'll bold. There's that correction factor. Now, I want to notice something just like last chapter, Chapter 10, when we had a bunch of calculations. Back in Chapter 10, we started to use helper cells to make our formulas a little bit easier. Not only that, but we're going to use it later in some other calculations. So let's go ahead and do that. Equals, hey, there's population proportion 1 times, well, we already have the 1 minus right there, and divide it by our sample size. Control Enter. So that is the amount. Now we just do equals square root. And there it is. We already calculated that whole little inner bit. Close parentheses, and we have to use our correction factor. Square root, open parentheses, and the top part of the numerator, big N minus little n sample size. Close parentheses. Now we have to divide, and the denominator, that's that part, open parentheses, big N minus 1. Close parentheses. One more close parenthesis, and there we have it. Control Enter. Now, this is the formula that we will use because we don't usually have all of the sample proportions to calculate the standard deviation from. That's going to be our estimate. Here we actually have our population proportions. Later we won't have them, but we'll use sample p to estimate. But remember, we had our population proportions here, 0.25 and 1 minus population proportion. And we have our sample proportion, so we can just prove that this formula works, just like, of course, we did in video 63, chapter 10. And we're going to use standard deviation of the population. Because remember, when we listed every single possible proportion, that is the population. All right, you ready? So I'm going to Control-Shift down arrow and then Shift-Enter. And you got to be kidding me. Look at that. There's the formula we use to estimate it when we don't have this full distribution. If we have the full distribution, which is basically never, we go ahead and calculate it straight from the source data. And they're exactly equal. Hey, in this first part here, we just showed that our expected p-bar is exactly equal to population proportion, and that our formula actually does get the right answer for the full distribution standard deviation. Going back over to our PDFs, we can see, hey, there's the two formulas. We just proved that both of these formulas work. Now, this is page 2. If I page up and go to page 1, this is the distribution we want to create now. Now, remember, sampling distribution of Pbar1 minus Pbar2. That means every single possible difference between these two sets of p-bars. So if I go back over to Excel, and I'm going to scroll out, Control, and Roll, I've done the same exact calculations for a second set of population yeses and nos. Now, what does it mean from a set of all possible sample proportions for population 1 and all sample proportions for population 2? What does it mean to get every single one of the differences? You actually have to take the very first sample proportion and subtract from it every single one of these. That would be 1, and subtract 56, because there's 56 of these. Then you'd have to go to the next one and subtract all 56. That means new 56 set of differences, right? So just for the first and second one, that's 2 times 56, 112. Then you'd have to do it for the next one and the next one. Now, last chapter, we saw a crazy formula. And we actually didn't see the formula, but there was a reference video. And I've already done it here. So check this out. If I highlight all the way down, remember, that's just the first sample proportion from population 1. There it is. I've highlighted them. And you could see down here, it says the count of 56. So I had to list that 0.2 56 times. And then all of these, that's the exact set of 56 proportions, 0.2, 0.4, 0.4, all of these from our second set of sample proportions. So once you list all those, and actually, if you're interested, Control down arrow. I actually made a different video since I shot chapter 10, Excel Magic Trick 1205, that shows this exact example and some crazy formulas to list this, which are not required for this class. But there it is in case you were wondering. Control up arrow. Now, we've listed every single difference. And actually, the total, that means how many differences we have, would simply be 56 from our combinations for population 1 times 56 here. And if I scroll over and hit Enter, it's 3,136. So I've done that many differences. All right, you ready? Equals, and I'm going to take the sample from population 1 and subtract the sample proportion from population 2, Control Enter, and double click and send it down. That's every single one of the differences. Now, there's a couple things we want to learn from listing this entire distribution of differences. Now, the first thing is I went ahead and made a pivot table from this data set. And because there's so few different unique differences, I just dropped the difference field into the row labels and then into the values area and counted. And look at this. There's our pivot table. There's our count. And then I made a histogram. Now, we've done this lots of times earlier in the class, so we're not going to do it here. But notice the shape is pretty close to symmetrical. So from our complete listing of all the differences, the distribution is going to be always pretty symmetrical. The next thing we want to do is we want to calculate the mean of all these differences. But before we do that, let's calculate the actual population 1 proportion for yes and subtract the population proportion for yes from the second population. So you ready? Equals, and I'm going to scroll way over. All right, so our proportion P1 for yeses from population 1 is 0.25. And you could see the formula forming up in the formula bar. I'm going to type a minus sign. You can see it happening up in the formula bar. And now I'm going to come over here. Here's our second population. There's our P sub 2, which is the population proportion for population 2. Whoa, 0.375. So that was a proportion of getting a yes. And there's our formula. I'm going to hit Tab. That'll kind of jump me over here. And there it is. The actual population difference between those two proportions of getting a yes is minus 0.125. Now let's do the drum roll, the mean of all the differences. We're going to take the average, click in the top cell, Control Shift down arrow, and Shift Enter. And lo and behold, look at that. It's exactly equal to the population difference. Now, the next thing we want to do is we want to do our formula for our standard error. Hey, but guess what? We have all the source data. We almost never have that. But I'm going to calculate the standard deviation. Remember, this is for population because that's every single possible difference. Click in the top cell, Control Shift down arrow, Shift Enter to put it in the cell and jump up. And there it is. 0.91. That is the standard deviation for the sampling distribution of the difference between our two sample proportions. Now let's do our big long formula. And luckily, you can see it here. It's inside of the first square root. Population from proportion 1 times 1 minus that divided by n, and then adding it to the same calculation for the second population. We've already done both of those calculations in the cell. So I'm going to say equals square root. And I'm going to have to scroll over here. And there it is. So in cell G7, I can see I have already calculated that. Now I'm going to type a plus symbol, and I can see it popped up into the formula bar. Now I'm going to come over here, and there's our same calculation for population 2. I can see my formula up here. Close parentheses, and I'm actually going to scroll over. And now I can see the formula right here. And so now I have to do the rest of that time. This is the correction factor because we have such a small sample size and population size. Square root, open parentheses. Now I'm actually going to use the population. And if I scroll over a little bit, you can see this is N2, but they're both the same. So big N, that's population size, minus, and I'm going to get the actual sample size. It's the same for both, so I can use it. I'm using it from our population 2. I could have easily used it from population 1. So that's close parentheses, the numerator, divided by open parentheses, big N, minus 1. Close parentheses, and here's the drum roll. Control Enter, exactly the same. So we did a lot in this video. The ultimate goal was to actually create the entire sampling distribution of Pbar minus Pbar, listing every single possible Pbar minus Pbar. We showed that our formulas look like they're going to be working. We had a basically symmetrical distribution when we plotted our entire distribution of our differences. We also went back all the way to Chapter 7 and saw how to list every possible sample for categorical data and calculate every single sample proportion. And then we saw that our two formulas worked there. Now, our next video, we will talk about confidence interval and hypothesis testing for two population proportions. All right, we'll see you next video.